Alright, sorry about the background noise. I am going to just try to ignore it. Basically, today, since yesterday I finished the neural Turing machine content addresser, I'm going to start work on the location-based addressing system of the neural Turing machine, which the first model needed in that, in the creation of that, is, let me turn on my laptop, it should be the Interpolate model. Okay, yeah, NTM Interpolate is the next model that I'm going to make. So let's just go ahead and start. First things first, I'm going to make the header. You know, maybe Interpolate would actually be something that we could generalize and use it a lot. Interpolation between two things. I'll just make it generalized interpolate. So we are going to be interpolating between two vectors, and so the input is going to be a matrix. Public model fields. I love that macro. That's by far, like, it's by far my favorite macro in Aurora. I don't actually know if that's true. I think I'm gonna take that back. But it's a pretty damn good one. Interpolate. Perfect. Now let's go ahead and make our CBP file. And now that we have our CBP file, go to our code generator. This is going to be called Interpolate, and let's go ahead and run the code generator, because it's not like a human wants to do this. I mean, literally, I'm running the framework and I don't want to, so it's not like anyone else is going to. It's not like anyone else is going to want to. Jesus. Yeah, so anyway, let's get our header on the right hand side of the screen. This constructor is going to have size t a units. We're going to say units is equal to a unit. We also need an amount by which to interpolate, by which we should interpolate. So public, and I'm going to make this tensor amount. And then we're going to have amount gradient. Perfect. Oh, yeah, we'll initialize those later. Parameter-wise, that won't do anything. Clone. Units is the only field that we need to copy over. And let's not worry about forward. Just like that. The output is going to be a vector, and so the desired is going to be vector y sub 1d a y desired into y grad. Each one of these little models is so damn concise and straightforward to make. We'll see when we get to the forward and backward functions if that holds. But I mean, I'm just saying, as of now, that's a really nice feature of modularizing the code like this when going into making the neural Turing machine. Recur. There are no smaller models, but we could do a func this that can be applied to this model. Okay, compile. So first things first. Tensor new 2D. There are going to be two vectors that are interpolated between, and each one's going to be a size unit. X grad's going to be the same thing, but then y new 1D This is simply units. thing. Then we have amount. New 1D1, 1. Just like that. And now what we can do is we can say y at I is going to be equal to x0 at I times essentially amount at 0, and I should probably specify essentially amount at 0 is just amount. It's the amount. There is no other elements. There isn't like a 1 because we initialized amount to be a tensor, a vector of size 1. The 0th element is the only element in that vector. Plus, and this is essentially going to be 1 minus, I think at first I should do x1 I times amount at 0 is going to be 1 minus the amount at 0. Now we have to specify that amount can only be between 0 and 1 in order for this to make sense. So maybe we should throw an exception if amount is ever beneath 0 or above 1. Oh my gosh, I keep right-clicking. I need to let go of the mouse. Jesus. If you think about this, every iteration we're indexing the same exact place in the vector, so we might this is an optimization. The interpolate amount. Looking good. So now when we have backward, what do you think? Okay, this is where I'm going to need to do some quick calculus. Oh no, I turned off my laptop. To try to figure out what the gradients would be. Or the derivatives. Okay, I think I did the calculus. So first things first, let's get our interpolate amount. And then this is not a sequential model, so we can iterate forward, essentially. And we can do, oh, you know, this is going to be multiple things. You're going to need braces. Since the 0th vector, every element in that vector is being multiplied just by the interpolate amount, we're going to say that x grad 0 at I I see room for optimization, and that is the amount complement. And I mean, I hate having to deal with multiple types at once, so let's just make it double. And there we go. 1 minus the interpolate amount is the amount complement. And so now we can multiply this by the amount complement. Oh, we should also it's kind of funny. x0 I. Okay. Wait, no. Ha. Not good. Have to make sure you end up linking it up to the loss in some way, so that's y grad. That's where that comes in. Let's go ahead and test this now. And really quickly, we're going to add it that. Oh! We don't need a bias. Jesus. Let's go ahead and fix that. We don't need a pseudo neuron softmax. We just need actual sigmoid. Like new sigmoid. That's it. We output 0.5, which was the 0.5? Wait. Why was the amount 0.5? Oh, you know? That's why. It's because softmax's x started out as 0, and the softmax of 0 is 0.5. Nice. Well, I mean, it found 0.7 pretty damn quick. To be honest, I don't know how fast it found it because the output is too slow. So if I do sleep, slow it down a bit, see how fast it finds it. It's nearing 0.7, which basically translates to, if I hover over this, softmax's x .84. Like if I grab that value, and I dump that into Desmos, the value, the y should be exactly 0.7. Wow. All right. Very cool. That is very cool. Okay. Well, I think, did we prove that it works? Yeah, sure. I want to make this a little bit more like rigorous of a test, though. So should have x be a randomly initialized matrix of size 2 by 5, which it is, and y should be essentially the interpolation between the two according to the desired amount. And now, if we just let it run, it should near 0.7 once more. The only reason that I did that is because I want to be able to test other values than 0.7, and going through Desmos takes so damn long. About like 0.2. How about that? So it's decreasing, and it should asymptote at 0.2. Wow. This is sick. Okay, so this model seems to be working.